Welcome to this new session. As I said before, you might be producing questions by delivering emails either to Santiago Arias or Rafael Guedes. In here you have the emails, the addresses where you can produce the questions. In that session, I'm going to be speaking about the different technologies, the different methods of converting the solar energy into electricity by using the CSP technology. And there are many different concentration concepts. I will be speaking about the Stirling dishes. I will be speaking about the Fresnel concentrators. I will be speaking about the beam-down system, parabolic trough concentrators, and finally the tower configuration. But I need to tell you something. I'm not neutral. I'm not neutral because in the last 10 years of my life, I've been working on the last two kind of plants, on parabolic trough plants and tower plants. So maybe I'm much more, let's say, tower-oriented than on the rest of the technologies. My idea is you to pay attention on what I'm going to be and when to say, and yourself could create your own criteria when I speak about the plus and contrast or the advantages and disadvantages of every individual concentration concept. So the first technology I'm going to be describing is the Stirling dishes. Stirling dish was very popular when the PV price, or was looking very promising when the PV prices were very high, and has shown clear and evident advantages. The first one is that it's very, very efficient. A Stirling dish is really a structure, a metal structure holding mirrors, and is designed to be facing the sun. I mean, tracking the sun in the sense of just being tracking the sun and presenting the whole surface of the dish directly to the sun. So in any time of the day, it's going to be receiving a maximum amount of energy in that particular area. And then this surface is again composed of reflecting material, and what happens is that the sun rays are going to be concentrate obviously in the focal point of this 3D parabola. In that point they installed a Stirling motor. And I would like to describe the Stirling engine, because this is something which is difficult to, it took me some time to understand how it works. Let's say that it's a thermal engine that was conceived, was designed at the first time as the diesel engines or the gasoline motors in the early 90s. But then was not developed. There is not too many applications for those motors. So let's say that the automotive industry has been using I don't know how many million of diesel engines or gasoline engines for the automotive industry and for the aeronautic industry, and maybe in total Stirling motors have been only 60 or maybe 100 have been constructed for very specific applications. But it's a very interesting engine. I mean, first of all, it's an engine having no exhaust. So it means that the gas which is inside is compressed and is expanded inside the motor without any flow of air coming up and down. So it's an external heated device, and it's the gas which is internally allocated in different parts of the motor, the ones making and forcing the flywheel to rotate. And really it is composed of two pistons, two cylinders. One of them is the one which is heated. Obviously in the case of the CSP applications, this is the hot spot where the light is concentrated, and then you have two chambers. One is located in the hot cylinder and the other in the cool cylinder, obviously having a certain refrigeration or a system, normally water or something like that, to refrigerate that piston. And then the gas is moving from one cylinder to the other. So obviously when all the gas is in this hot cylinder, the gas is hot, so it is expanded, and there is a relevant pressure, internal pressure, produced to push that piston. From there, the gas is moving to this other cylinder, and then it's cooled and contracts. And then when contracting, it's obviously producing a lower pressure in the system. And this variation of pressure from being very high to being very low is what it forces the flywheel to rotate. So it's a very strange configuration. And again, was designed more or less at the same time as the diesel and the gasoline motors, but has been not massively produced. And that's my first concern, is that has never been industrialized. The prices are very expensive, and the reliability of the motors is questionable. But I will say that the steel in dishes has some advantages and some disadvantages. The first one is that it is a modular configuration. I mean, you can buy a single one to be installed on top of a building or something like that, providing like 150 kilowatts of electricity, or you might install 2,000 of them in a solar field to produce megawatts of electricity. So this is a very good point, because by being modular, you might reach many different applications, and also because it is modular. Obviously, modular means that you might finish producing a huge amount of elements, and then producing a huge amount of elements means that the industrialization process could be achieved, so the mass production is achieved, and the prices normally will tend to go down. Another advantage is that, again, theoretically, the Stirling dish can reach very, very high temperatures, and so according to the thermodynamics, it could produce electricity having a high efficiency, maybe in the range of twice or 3 times the efficiency achieved by a PV panel. And all that is very good, and all that is very positive. However, there was no proliferation of this kind of Stirling dishes. There are very few installations in the world, and my impression is that this is a dead project, meaning that it will no longer be used. And the reason was, first of all, some problems related to the durability of the system. Some friends of mine, well, some people I know, were purchasing like 6 units just to test what happens with the Stirling motors, and in less than a year, 4 of them were failing. So this is obviously something that you don't want to happen when you are installing it. You have to install 2,000 or 3,000 of them. The other issue is that obviously you need to be being very precise in tracking the sun. And really speaking about that picture, or looking about that picture, I don't think that that kind of wheels moving on the concrete are the best devices to produce a very accurate movement. And also, obviously, that produces high maintenance, all these rotating structures and things like that. Remember that this is like 6 meters wide, so this is a heavy structure. So it requires a lot of maintenance. On top of that, there are some cleaning difficulties. when you are operating a plant, cleaning is an issue. I mean, you have to be cleaning the solar field at least once per week. And imagine that how to achieve an automatic mechanism to be able to clean properly that surface when the surface is, let's say, hidden in between all these bars and all these systems. I mean, you need to be approaching that surface to clean that surface without interfering or with the danger of interfering and damaging the Stirling motor or something like that. Cleaning, I think, is a big issue for those devices. By the way, cleaning is very relevant on CSP. I mean, obviously we are reflecting the light by using mirrors. A mirror has a very high reflectivity factor, meaning that a good mirror is able to reflect 97% of the light which is received on the surface. But obviously, dust accumulation is going to reduce that efficiency to values that at least we have measured. That in Spain, for instance, in the south of Spain, it means that we drop something at 6% per week. So we try to maintain the whole system very, very clean to maintain the efficiency of the system. To me, even when there are some technical difficulties like the tracking difficulty or the cleaning difficulty of the high maintenance of the system, to me the worst thing about that system is that you are not producing a manageable energy, meaning that you only produce electricity when the radiation is very high. And if there is a cloud passing through, immediately you are going to be not producing electricity. So the situation is not very good for the grid. I mean, you are delivering when the sun is on, but you are not producing when there is a cloud. And which is even worse, you are not able to produce at 9 o'clock. And again, I want to repeat that. If you are not producing at 9 o'clock because it's night time already, it's dark, you are not producing at the time that the consumers are mostly using electricity. So this kind of device, the Stirling dish, is actually competing directly with PV. And then, well, maybe the engineers are going to say, well, but this is more efficient than PV. And the answer is, okay, instead of putting one PV panel, put two. And the price will be cheaper. Obviously, the operation will be easier, and you are saving a lot of problems just by duplicating the number of panels. And since the PV panel price has dropped so dramatically, really today there is no commercial applications involving Stirling dishes. In the past, there were some projects in the USA to install hundreds of those dishes in the desert. All those projects were cancelled, and in fact the projects were converted. Instead of using Stirling dishes, now they are using PV panels. Another very interesting system is the Fresnel system. Later on I'm going to be speaking about the parabolic trough, but this is a system which is emulating the parabolic trough. Instead of having a real parabolic shape, tracking the sun and concentrating the light on the focal point, what you have here is some flat glasses, but then those flat mirrors are oriented in a way that they are emulating an actual parabol. So each one is going to be taking a different angle depending on the position of the sun to reflect the light of the sun and to be like a parabol. The system could be very, very cheap compared to other systems, and it's a very interesting device. I like the concept because it's very simple. I think, well, obviously it is easier to find out a piece of flat glass rather than a curved glass, which needs to be emulating a parabolic parabol shape. But it's okay from the concentration standpoint, but obviously it's emulating. So in some circumstances, in particular when the sun is in the zenith, the system is very well replicating a real parabol concentrating the light on the focal point. However, you realize that when the sun is early in the morning or late in the afternoon, is close to the horizon, obviously there will be some problems because one mirror is going to be shadowing the next one. So the efficiency in these conditions is far lower compared to the real parabolic trough, which is always oriented to the sun. This is not an issue, a relevant issue, because in this sector, efficiency is very important, but it's not the most important parameter. I always say so because for the time being, the solar energy is free, meaning there is no tax on using solar energy, which means that efficiency, which is the most relevant factor in every process worldwide, is not so relevant in that particular process because the denominator is costing us zero. So if the Fresnel system is less efficient as parabolic trough, but the price will be, let's say, a fifth of the parabolic trough, maybe that proposal, that idea could be very, very sound from the economical standpoint. However, the problem is that the actual installations, the maintenance and the cleaning is far more difficult as compared to the parabolic trough that has already developed automatic systems for cleaning the parabols. Mainly just because parabolic trough is much more popular, has been already passed through a process of industrialization that makes the price very competitive compared to the, let's say, the unitary price of making a Fresnel concentrator that in theory could be cheaper, but in practice is going to be more expensive compared to a parabolic trough, just because the parabolic trough has been produced so in so huge amounts that the level of industrialization has already been achieved, and they can offer those devices at very, very low prices. So again, as in the case of the steel dishes, there were a couple of projects operating with Fresnel concentrators. My impression is that this is a no-way device. It's a system that will be abandoned. In fact, Areva, Areva is a French nuclear company that was promoting the Fresnel technology, and recently declared that they are no longer going on CSP. So right now, practically nobody is promoting Fresnel technologies. Among the systems that are available, one which is very, very strange is that beam down system. Beam down means that you have solar field composed of heliostats, similar to the ones we use in the tower configuration. So those heliostats are going to be reflecting the light of the sun and projecting the light of the sun on this dome. But this dome is not the receiver. The dome is again composed of mirrors, so the light which is received is going to be again concentrate in a focal point located at ground level. And again, it looks like a good idea because you can achieve incredible high concentrations of energy. However, my impression is that even when that double concentration provides a maximum flux and the potential very, very high temperatures, my first question when I saw the device is how to clean that dome. Because obviously all the energy which is not reflected by this dome needs to be, let's say, dissipated. And just to mention, in a small plant like Gema Solar, in the tower, we are receiving like 140 megawatts of thermal energy. So imagine that in a similar plant having this configuration, if those mirrors are just having 5% reflectivity factor, you need to be, let's say, evacuating something like 7 megawatts of heat. So that obviously is a big problem. And since the dome is located up there, my question is that an easy system to clean? Because obviously if the dust is accumulated and you have a reflection in the range of 10% or something, 10% of the power that is received needs to be evacuated, and that's a lot of energy. Besides, I consider that the concentration is too high. I mean, you might be concentrating 1,000 times the solar radiation, but then you will be melting all the materials available. So my question is what to do with this high concentration of energy. So my impression is that this is just a pilot plant in Abu Dhabi that will never be converted into a commercial application. The other system I will be speaking today is about the tower configuration. But I've been purposely dividing that configuration into two different kind of towers. The towers operate with water and the towers operate with molten salts. Because even when the configuration is the same, the performance and the way we operate is 100% different. Regarding the tower configuration, using directly water, so producing directly steam in the receiver, the configuration looks like that. I mean, this is one of the Abengoas plants in Spain. You have hundreds of aerostats. Aerostats means just a structure holding mirrors. So the mirrors are reflecting the light and concentrating the light on top of the tower in a certain area of the tower where the receiver is located. So I want to emphasize that every individual heliostat in the solar field has to adopt a different angle, bidirectional angle, to reflect the light of the sun, aiming to a certain point. Since the relative position of the heliostat versus the target differs from this heliostat to any other heliostat, also the angle to obtain the light concentration in the target, also the angle has to be different. So in the whole solar field there will be no two heliostats having the same angle. Each one has to have a different mathematical law or something to do the job. I mean, to adopt the right angle to be reflecting the light on the target. Well, once you have the accumulation of energy in the back of this tower, there you have a receiver, and a receiver is like a radiator. So you are passing water through the radiator internally, I mean through the tubes of the radiator. The external part of the radiator is receiving the solar energy, and obviously the water will become steam, and then high pressure steam in fact. So directly in the tubes of the receiver, you are going to be converting the water into high pressure steam. Then the steam is delivered to a turbine, and the turbine will be immediately generating electricity. So I like the system because it's very good. I mean, it's very simple. You are not needing any heat exchanger in between the media which is heated by the solar field and the water is directly the water which is used to pass through the tubes of the receiver to generate directly the steam. So everything is simple, is cheap, but has a big problem. In the case of the plants I know, first of all, you are generating steam in the receiver, and that has some difficulties from the technical standpoint. The receiver is exposed to very, very high temperatures, but is variable temperature, meaning that during the night obviously will be cold, then during the day is reaching impressive temperatures. So let's say that the tubes are exposed to, let's say, difficult conditions due to the change in the temperature. But on top of that, in that particular receiver, you are generating steam. Steam at high temperature means high pressure steam. So you have to have a system to a receiver which is able to withstand the changes in the temperature as well as internal pressure, very high internal pressure. And this is adding complexity and providing problems of cracks and things like that on the receiver itself. Nothing to say about when this is happening not just at the let's say expected moments, but just because there is a cloud which is moving in the horizon and you don't know exactly if it is going to be affecting you or not. So in the middle of the day, the stress that can be produced just because suddenly the cloud is going to be removing the energy and reducing the temperature of the receiver is something which has a relevant effect on the durability of the receiver. Again, there are 3 or 4 plants in the world using that technology, which looks very promising, in particular when the PV prices were higher than today. But right now, we consider, well, not only we, everyone in the sector considers that nobody is going to continue making towers like that because the capital cost as well as the operational cost are far higher as compared to PV. And then why to do something so complex when using a PV panel you may achieve the same result without creating all these complex plants, because they say, well, we store a certain amount of energy. You know, here in this plant, the steam is not going directly to feed the turbines. There is a small storage system which is composed of 2 high pressure vessels to contain enough steam to operate the turbine for some minutes, meaning this is absolutely necessary to be able to stop the turbine in a let's say normal procedure and not just destroying the turbine on the first time you have to stop the receiver, because the turbines do not want to be changing the conditions fast. I mean, a steam turbine is something that you need to graduate the descent of the temperature and the pressure and everything. Otherwise, you are damaging the internal parts of the turbine. Then those 2 cylinders are just able to contain enough steam to operate the turbine for minutes before stopping it completely. So again, since has no possibility of storage, that kind of plants are competing directly with PV, and PV is cheaper. So why to do them? In the next section, I will be speaking about parabolic trough and tower configurations that are the most promising ones. Anyhow, in case that you have some questions, I remind you that there is the possibility of delivering emails to Rafael or me.